As a final evaluation of basic lens properties, we will now briefly look at diffraction. So I've drawn here an optical axis with a lens in the lens plane, and the pink bars denote the opening of the lens. So we have a ray here that is projected onto a point in the image plane, or if we have a parallel beam coming in here, in the focus plane. And the angle that this ray makes with the optical axis is the maximum opening angle of the lens, which I denote by alpha. Now we know from Huygens' principle that each point on the lens aperture can be treated as a source of spherical waves. So we know for the position here along the axis, a wavefront can be drawn which travels along the optical axis. The same can be done for the ray that we have here. So here also we can indicate fronts which all propagate in phase. And this is for the upper ray drawn here. Now if this point is a focus point, the rays arriving from all positions in the lens plane will be exactly in phase, leading to a maximum intensity on this position. Now if we have another ray coming in under a slightly different angle, hitting the image or focus plane slightly below the other plane, we will not get maximum interference of the waves traveling from these different points, so the intensity will be reduced. And this reduction comes from a difference in path length for this wave compared to the wave we have here, or the wave that we have here. Now we're going to consider the point here, and we assume that we are still very close to the axis, so the distances here are very small, so that the phase of the paraxial ray that travels here on this point is the same as for this point. So the only path length difference comes from the difference between this ray and this ray. And we can see that path length difference depicted here. If we draw a straight angle here, and the delta x here is the path length difference between these two rays. Now we can see that the intensity will diminish as we go further away from the axis, and we will hit a minimum here in intensity when the path length difference here equals half of the wavelength. This is the point where the two waves are exactly hitting, so the wave coming from here and the wave coming along the axis are hitting this point exactly out of phase. Now I will denote the distance that we are here from the axis as d, and we can see from the equivalence of this triangle with the big triangle that we have here that the angle here also equals alpha. So we can now see for the triangle that we have here that d is related to delta x and alpha by the sine of alpha equal to delta x over d. Now we can see from the two equations that we have here that in order for this to be the minimum, d should be equal to delta x over sine alpha, or lambda over 2 times the sine of alpha. And this equation is our famous diffraction limited equation, which states that the diffraction limit, so the distance between a point here and the next minimum, is equal to the wavelength of the light divided by a factor times the sine of the opening angle.